Hello, everyone. Welcome to lecture 2 on finite element method. In this lecture, we want to understand the fundamentals of finite element method, or fundamentals or main ingredients of the finite element method using a fairly simple structural element like spring. So finite element method is, as the name suggests, is basically relying on the concept of discretizing the domain into elements. Okay, so you have a domain of a problem and then you discretize them to elements. So the first ingredient is basically elements, and then again, as the name suggests, that's not a surprise. Now, these elements, they usually have their own corners, and we call them nodes. And usually, your boundary conditions are imposed on these nodes. And then you solve your problem. So the way you solve your problem, or the reason that, or the approach that you use to solve your problem, that is the methodology of the finite element method. So it is very important to pay attention that in the finite element method, we approximate the space. So we discretize the space or approximate space, but that is not the only approximation. We also approximate let's say equations. Okay, so you shouldn't think that finite element method is simply something that, for instance, let's say this is the solution, and now you take this as the solution. This is not the finite element method exactly. Okay, this could be a branch, or let's say one of the children of the finite element method, but in principle, our approach to finite element method, let's say it could also allow for a solution like that, okay? So it's not simply just discretizing the domain and approximating the solution, it's also approximating the equation, and that equation approximation itself is in the method. Now, approximating the domain, it means you just discretize the domain into representative points. But again, that part is similar to many other methods, such as finite difference too. All right, so that's that. Just give me a second. Okay, so that's that. Now, after we do this, there is this next step that we usually call assembly. And that assembly takes you from element-based model, or from element-wise formulation to global formulation, okay? So let's say you have your element-wise quantities. In this case, it would be something like stiffness, and then you throw those quantities into your assembly procedure, and your assembly procedure gives you your global system. Now, it turns out that that global system is always looking like some sort of K, which we call stiffness matrix, times a displacement vector for the entire system. And on the right-hand side, you would have a force. Okay, so this would be your stiffness. This is your displacements. And then again, this is a vector. This is a matrix. And on the right-hand side, you have forces. Now, displacements and forces, as you can imagine, they are node-wise quantities. Okay, so you calculate them for each node. Let's say these are calculated at nodes. And then stiffness, on the other hand, is calculated at elements. Okay, so this is what you see in front of you is kind of the big picture of finite elements method. So basically what you do, you discretize your domain into elements and nodes, you apply boundary conditions on nodes, then you assemble the system. If you assemble the system, you end up with something like this. And that equation, it has, again, informations about the nodes, which are displacement and forces on nodes. And then it has stiffness of elements. You solve that system, you calculate the displacements or forces depending on what is known and what is unknown, and you are done. So this is the, let's say, the big picture of finite element method. Now, as I mentioned, a nice thing about what we want to do today is that we will be using springs just as examples. It's not exactly finite element method what we do today. We just solve some nice examples using springs. Okay, so again, it is not exactly finite element method, but using just a combination of springs, we would be able to identify these pieces of the ingredients of the key ingredients of the finite element method. If we just think of a system made of a bunch of springs, so if you just think you have, I don't know, let's say you have these two springs, then it's like you have two elements, right? So spring one, spring two, these are elements. Then you have three nodes. So these are the nodes. So we know the nodes. And then maybe you fix it here and you apply a force here. These are the boundary conditions. And then for each element, you can calculate the stiffness of the element. We can assemble them, we get the global stiffness, we get to this system, and we can solve the system. So these pieces of the finite element puzzle are basically covered using just a combination of springs. And that's what we want to do in this lecture. Do you have any question? Okay, so let's call this understanding key ingredients of finite element method using springs. So this is what we want to do. Now, in the previous lecture, as I mentioned, if you have a spring, let's say this is node 1, this is node 2, that spring has a stiffness K. You can imagine at node 1, the displacement of node 1 is U1, the displacement of node 2 is U2, the force at node 1 is F1, and the force at node 2 is F2. Now, two things you need to pay attention to is that first, I am drawing this little line here just to emphasize that our, let's say, our plus direction is towards right. So this is kind of our x coordinate system, and we are talking about a one-dimensional example. That's one thing. The other thing is that I am putting these indices as subscripts. I put it up. Previously, we put it down in the last lecture to keep it simple as, previously we put it as subscripts down, and today, and from now on, we actually put them on top as superscripts. So the reason is that later we will distinguish between quantities that appear on top of something or at the bottom of something. So if you have, I don't know, something like A, we may have some number n here, some number m here. Later, we will distinguish between the meanings of n and m. Okay, for now, it's not too important, but to be consistent with what we want to do from now on, let's keep that in mind. Okay, so that's that. And then we mentioned if you have a system like this, then you can write your two equations, and eventually you would have your system F1, F2 equals, let's say, K minus K minus K and K times U1, U2. This is what we learned from the previous lecture. Now, if you compare this equation with what we just had in the previous slide, it's basically the same thing. But here I have the F, the force vector on the right-hand side, and I have this one on the left-hand side. Through the lecture, I usually write it in the opposite direction. So I put F on the left and then the KU on the right. But it's exactly the same story. So it's exactly our usual system. And this is very, very simple, of course, but this is exactly the same story. So this is F equals KU. And once you have this, you can solve it basically. This is like a finite element method with only one element if you want. Okay, so there is only one element, and then it simplifies like this significantly. All right, so that's that. Now, what we want to do is to use this approach and compute the stiffness for spring combinations. We want to do let's say, the famous spring combinations and also do something more complicated. So the first thing we want to do is to do a spring combination like this. Let's say you have these two springs, K1, K2, and we want to ask ourselves, what is the effective stiffness of this system. And then again, you know the answer, I think, but that's not the idea. We do not want to just use the same strategy as we had done before. We want to do it the way we do it in a finite element method. And using this, we want to learn the assembly process. That's question one, let's say today. The second thing we want to do is to look into this system. And now this would be maybe K1. This would be K1, this would be K2. And while I am at it, maybe I put also these 1 and 2s as superscript to be consistent with what we just mentioned for today's lecture. So let's say this is K1, this is K2. Okay, and then again, the question is, if we have this system, what is effective stiffness? And finally, knowing this, and then again, these are easy or straightforward to calculate, and you know how to do it, but then we want to complicate the picture a little bit and do something that it wouldn't be so straightforward to answer based on what you know from the past. So let's say we want to look into this system then after that. All right, so this is now the last system we want to look at today. Now in this system, again, you have K1, K2 here, K3, K4, K6, and K5. Okay, so as you can see, the first two systems, based on your previous knowledge, you know the answer. They are pretty straightforward, but the third one is not. Now, in order to approach the third one, we first need to do the first two, but from a different perspective, from our own perspective of finite element method. And then using that, you learn the assembly process. You learn how to assemble springs. And then once we are done with this, which is again a little painful because this one is based on what you have done before, is pretty straightforward. The way we do it today is longer than usual, but then it pays off because once you learn how to handle this, it would be very easy or again straightforward to handle the third one. So let's do that. All right, so I'm going to start from the first system. That we drew together. So, okay, remember the first thing we did before and we mentioned as ingredients of the finite element method is not only to discretize the system into elements, it's also to discretize the system into nodes. So here you have two elements, but you should also distinguish between nodes. So the left node, we call it node 1, the right node, we call it node 2. Now, similar to what we have done before, the force at node 1, we call it F1, and the force at node 2, we call it F2. Now, how about the displacements? The displacement at node 1, we call it U1. The displacement at node 2, we call it U2. So what is the difference between the forces and displacement from this perspective? So you can see already that U2 is the same for both springs. U1 is the same for both springs, but F1, the force at point 1, is basically the sum of the forces from spring 1 and spring 2. So if I write that, then basically I can say F1 would be F1. Let me just do it in a, in parentheses. And the parenthesis, it basically indicates that the quantity inside is the element number. The same for F2. So F2 is F2 from spring 1 or from element 1 plus F2 from element 2. All right, so this thing, it means from spring, so it's a spring counter, okay? And then the first superscript, this one, this is the node counter. So it's at which node coming from which spring. All right, so this is your system. Now, we analyze the system, or we split the system into these two springs separately. Let's say you do spring 1. And you do spring 2. Okay, so from spring 1, if we want to write exactly the same system, so we want to write this thing for each of these springs. So if I want to do that for a spring 1, I would have, on the force vector, I would have F1 from spring 1, F2 at node 2 from spring 1. Equals K1 minus K1 minus K1 and K1. And then this is U1 and U2. Okay, so what we did is exactly what we had here. We just adopted exactly the same strategy. Okay, now I do the same thing for spring 2. Let me just organize this a little. Okay. So now if you do the same thing for spring 2, it's very easy. You can exactly take what we have written up there and rewrite it again, but we need to sort of adjust for these numberings. So here, remember in the parentheses, we said the quantity tells you from which element. Now, This would be from element 2. And the stiffnesses are, or the Ks are the Ks of spring 2, but the U remain the same U, okay, because it's for the system. All right, so we have this thing so far. Now what we need to do is to combine these together, and that combining them, it basically means assembling them. This is exactly what we want to do in the next step. The key to assembling them is exactly what we have here. So I'm going to do that in the next slide. So let's keep this, but I'm going to shrink it a little to make space. Okay, so we know this. Now what we want to do is to assemble these two. And as I mentioned, the key to assembling them is to pay attention to the idea that F1, F2. So if you wanted to construct a force vector for the system, so the force at node 1, so this means force at node 1, and this means force at node 2. Now that thing would be the sum of the two forces at each node from both springs. So it would be basically F1 from spring 1 plus F1 from spring 2. And this would be F2 from spring 1 plus F2 from spring 2. All right. Okay, so now that you have this, all you need to do is to impose this or to feed this information to what you have on the left-hand side. And by doing that, you would get something like this. So you would have a system which now has F1, F2 here. And if I use the informations or the equations we have here, it's basically adding these two systems. And if you do that, you would end up with something which looks like, okay, it would look like K1 plus K2 on this upper left corner. Then upper right corner, you would have minus K1 plus K2. Again, here you would have minus K1 plus K2. And then here would be K1 plus K2. And now this is U1 and U2. Okay, so now if you look at this system, if you compare this system with the system that we just had previously, like this, or like this, or the one that I mentioned at the beginning of the course, it's exactly the same structure, except that what you have here is a slightly more involved, and that is your effective stiffness. Okay, so that's the effective stiffness of the system. So basically what happens is now I'm going to shrink this a little and write it like that. So we have this, and from that, again, the first thing is that you will see our sort of our unified, our canonical representation F equals KU. This should always hold. This is, again, this is very fundamental to finite elements. But also you can see that in view of our definition of stiffness, you can think of this thing, again, if you think of this as being the effective stiffness of the system or the global stiffness of the system, this should have a structure which looks like K effective minus K effective minus K effective and K effective, where now K effective is a scalar value of K effective, right? So this is the matrix, stiffness matrix, effective stiffness matrix, and these are the components. And then again, if you now compare it with any of these, it clearly tells you that K effective is K1 plus K2. So that's what we learned. That's what we just finally have proved together. Okay, so this system, we just proved that K effective is K1 plus K2. That is the first question we wanted to answer. Okay, so this is the first system. Do you have any questions? It's very simple, right? It's really not super complicated. As you can see, the steps are very intuitive. But as I mentioned, this very, very simple example is extremely important to help you understand a very important and a fairly complicated concept in finite element method, that is assembly. It's very difficult to teach assembly, but you will see that using these, let's say, rudimentary examples, we will understand the assembly process perfectly at the end. Okay, so this was, say, example 1. Now we go back to that slide. So we come back to this slide. We did this. We know the answer to that. What we want to do next is the system 2. I'm going to clean again. Additional stuff. And we will do that again. So let's put the system here. Now, similar to the previous one, we need to identify nodes on this. So this would be node 1, maybe, node 2, node 3. Obviously, numbering them is optional. So it's arbitrary, basically. You can choose any numbering you want. Okay, now the same thing as we had before. So at each node, you have forces, you have displacements. Now here I have force F1, force F2, force F3. And these are, by the way, external forces at nodes, okay? So these are external forces. And then you have the displacements. I go back to use the same colors so that you kind of can compare them nicely. And then here you have U1, U2, U3. Okay, so now if you have this combination of springs or springs in series, previously this was springs in parallel, right? So this is, maybe I write it here. This is spring combinations or parallel combination of spring. Parallel combination of springs. In the next one, we want to have a combination of springs in series. Okay, so now what do we do with this one? The first step is exactly identical to what we have done previously. We take each of these springs and we write their stiffness. Okay, so what I'm going to do here is simply to write the stiffness for each of the springs. I kind of copy it from the previous slide to save time. So this is the stiffness for each of the springs. But now the difference is that the forces are not like that. They are simply just the forces in each spring. Okay, so we need to think about that. Now, on spring 1, this is a spring 1, force F1 is just the force coming from, let's say it's at node 1, it's just one force, okay? So it doesn't have that parenthesis in front of it. But for the second one, you can imagine that F2 here, when you want to write F2, now you would have 2 or F2 coming from 2 springs. So you would have, similar to what we have done before, you would have F2 from spring 1 plus F2 from spring 2. Okay? So that's that. What that means is that for the first spring, you need to write this 1 here. For spring 2, now we do F2 from spring 2 and F3. So this is the spring 2. And then the nodes here would be U2 and U3. Does that make sense? So basically what we do here is now, again, if you just look at this spring, the stiffness is just the stiffness of that spring. The nodes are U1 and U2. So node 1 and 2. The forces are the force at node 1, which is, there is only one force, and the force at node 2, it has 2 parts. It has a part which comes from the first spring. It has a part which comes from the second spring. So that's that. Okay, so you can see this is slightly different from the previous one, because now here you have U1, U2, and here you have U2, U3. And then also for the forces, you have F1, and okay, these two Fs are on the same node, but then you have F3. So the stiffness of this system is not going to be 2 by 2, it's going to be 3 by 3, because you have 3 points or 3 nodes. So we want to write that stiffness. if I write that stiffness, it's going to look like this. F1, F2, F3. And now again, these are like external forces, Fs, on those points, equal. We want to put something here, and then here on the right-hand side, we would have eventually U1, U2, U3. So this thing, it's now your, again, stiffness matrix. And if you want, this is kind of your global stiffness matrix, in contrast to what we have here as local stiffnesses. So these are element-wise stiffnesses. And then again, why am I repeating this so many times? I know I'm repeating it too often. But if you just look at what you have in this slide and what we just mentioned at the beginning about the structure of a finite element method, you can exactly see these ingredients again. You see there is an element-wise stiffness. We assemble them, we get the global stiffness. We have elements, we have nodes, we have boundary conditions. So all these key ingredients are here. And I think this is a very nice exercise to explain how you now take this, how you calculate the global stiffness matrix, and then calculating this, the way that we do it is exactly the same procedure that we call assembly. So we need to assemble that. So what would I need? The stiffness, if you just look at the systems you have, I create a new slide and then I choose different colors to do this step more carefully. Okay, so let's choose a green color for spring 1. And then maybe blue for spring 2. Okay, now on the global stiffness, we would have to bring all these green quantities and all the blue quantities. And we should put them into their correct places so that the assembly process is done. So now you can see that the green components, they come here. So there would be K1 minus K1 minus K1, K1. So as if you have a little system here, you see? This is basically your green system. Because now this would multiply with U1, this would multiply with U2, you get F1. So this is exactly what you would have here. And then the same with the second one. Okay, what the components from the green system. Now, if you think about the blue system, the blue system is going to be here. So it's going to be a connection between points 2 and 3. So we want to also do that now. The green system would be here. That means the blue system, sorry, the blue system would be here. So that means you would have the components K2 minus K2 minus K2, K2 here. And then on the off diagonal, these components on the far ends, they are 0. So there is no direct connection between spring 1, between node 1 and 3, right? That's why this thing is 0. So you should look at it this way. This component, the component you see here, is basically a connection that you would have between these nodes, okay? Or let's say this pair would multiply with this pair. So it's a stiffness between U1, U2, okay? Now, because there is no connection, there is no spring between point 1 and 3, you would get a 0 here, okay? So there is no stiffness there. All right, so this system that you see in front of you, this is the global stiffness of the matrix. And the way we just did it, or the process that we just did it, it's called assembly process. And then again, here, because we have just 2 elements and 3 nodes, we did the assembly visually based on what we see in front of us. Later, we learn how to make this automatic and how to program it so that the code understands how to assemble the system. But for now, it is important that you understand what we are doing. So basically, what we want to do is to put the green and blue system together, and then putting them together, it gives you this. This is very important, and you can appreciate this difference better if you compare it with what we had here. Here, we also did the same thing. We had, let's say, system 1, we had system 2, and then we added them together. But in this case, this addition, this assembly was more straightforward. So we didn't have to paint them in different colors and so on, but it's exactly the same thing. So if we had this, for instance, as a blue system, these are exactly our blue components. And then this would have been our, green components. Okay. So basically we did the same thing, but in this case, it's like these 2 systems, they sit exactly on top of one another, and that is different from this one. In this one, they are not exactly sitting on top of one another. All right. Do you have any question? It's 9:20, so let's have a break for 10 minutes, now 9 minutes, and we continue at 9:30 sharp. Okay, so we continue in 9 minutes. Okay, so welcome back. Now, we have a system in front of us as global stiffness system, but this is not exactly what we expect or what we expected to see, because usually, if you remember, for a system like this, we knew that we wanted to see something like 1 over k effective is something like 1 over k1 plus 1 over k2. We don't yet see that. Something is wrong with my pen. Just give me a second. Yeah. So we don't exactly see that because we need to do still something with this system. And that's what we are going to do next. Just okay, so I'm going to keep this and clean the the first parts, the trivial parts, and we need to work on that a little more. So let's do that, and then I think now you know that this one, and this picture I think you know it already, so I'm going to also clean this. Okay, so this is so far what we have. Now, what properties or what constraint should we add into this to make it a spring combination in series, right? So that's the goal. It's not exactly a spring combination in series because we have different forces here. We have F1, F2, and F3. If you remember, F2 must be 0 for this spring combination to count as spring combination in series, right? So we haven't imposed that constraint yet. We haven't yet imposed that F2 must be 0. And that's what you need to do now. So what we want to do now is basically take the same system, duplicate it, but now impose here that F2 must be 0. Now, setting F2 equals 0, it gives you a new equation that you need to impose to the system as a constraint, and then you can proceed with that, and that's what we want to do. So this is our new equation, and we want to just write it, let's say, clear, and see where we get. So basically what we see in that equation is that minus K1 times U1, so this times this plus this times this plus this times this is 0. That's what we want to write. So minus K1 U1 plus K1 plus K2 times U2 plus, and sorry, minus K2 U3 is 0. This is our constraint equation. Now, if we play with the terms a little, so I'm going to just take these two to the right-hand side. If you do that, you would see K1 plus K2 times U2 is K1 U1 plus K2 U3. Now, this is quite nice because it tells you that you can write now this system without U1, without U2, right? Because now U2 would be just a function of U1 and U3. Okay, so it tells you that U2 could be calculated as K1 U1 plus K2 U3 divided by K1 plus K2. All right. So I want to now play a little game together with you and see what we can get from this. So this is what we have so far. So we know this is U2. Okay, so now let's imagine we write a system . using this constraint. Okay, so let's say what we did here was looking into the second line. Now what I want to do is to write the first line and the third line and then impose this constraint into them and see where we get. Okay, so I want to write F1 and F3 and see what happens. So F1, let me just push this a little up to make space. So F1 would be, you see, F1 is K1U1 minus K1U2 is K1U1 minus K1U2. But now instead of U2, I want to use the relation that we have up there for U2. So this is the idea. Then you get K1U1 minus K1 times K1U1 plus K2U3 divided by K1 plus K2. So if you do that, you would get something like, you would have the, let's say, the common denominator K1 plus K2. Then you multiply that by this. So you would have K1 times K1 times U1. I'm not going to write K1 squared because we have already too many superscripts. So I write it as K1 times K1 plus K2 times K1 U1 minus K1 K1 U1 plus, or again, minus K1 K2 U3. Okay. And if you just pay attention to this, these two terms will cancel with each other. Then you would have a term which looks like that. Okay, it would be K2 K1 minus K1 K2. So that's what I want to do now. Okay, so I'm going to just repeat this page and so let's say this was our first conclusion, and now we are playing with the F1. And now if you look at it, and so if you just go one step further, you will see you get something which looks like K1, K2 divided by K1 plus K2 times U1 minus U3. Okay. So this is F1. Now, what we want to do is to play the same game for F3. Again, I'm going to just repeat it like that. So let's say we have the first one, the first relation here. I want to keep all of them in one slide because I think the final conclusion is very interesting. So this is the first thing we did. And now this is the second conclusion we just had. And now what we want to do is to repeat the same thing for K3, for F3, sorry. For this one. And I'm going to write it in green color. No, not green. A different color so that it's going to be distinguishable. Maybe this gray. So F3 now would be 0 times U1. So it is 0 times U1 minus K2 times U2 plus K2 times U3. So it's minus K2 U2 plus K2 U3. Now what we do is exactly the same thing as we did before. We are going to replace U2 from the equation that we have up there. So U2 is going to be minus, well, U2 is K1 U1 plus K2 U3. I hope I'm not making any calculation mistakes, but even if I do, we can tell from the final results. We kind of know what we want to get. So it's that, and then if you calculate the common denominator, again, K1 plus K2, you would have minus K2 K1 U1 minus K2 K2 U3 plus K1 K2 U3 plus K2 K2 U3. And then again, these two terms, they will cancel together. So you would end up with something which looks like K1 K2 U3 minus U1. So if you do that, you would get something that looks K1 K2 divided by K1 plus K2 times U3 minus U1. All right, so this is basically what you get from that equation. And now again, if I just make one last copy of this slide and put these things together. So that's that. That's your F3. Now, just looking at what you have and what we had previously, remember at the beginning of this lecture, we talked about this. So F1, F2, if you have a spring, F1, F2, so the force on the left and right on node 1 and 2, it would be K minus K minus K, K, U1, U2. You basically now have the same structure, except that it's not between node 1 and 2, it's actually between nodes 1 and 3. So it's as if you have a system which looks like this. F1, F3, okay, maybe I can call that K effective now. K effective minus K effective minus K effective, K effective times U1, U3, where K effective is defined as this. So this is your K effective. Or, well, it's the same thing. Okay, you can clearly see it, right? F1 is K effective U1 minus K effective U3, right? It's exactly this relation. And then F3 is minus K effective U1 plus K effective U3. This is exactly this system. Okay, so you can see now if you have a combination of springs in series, and that, again, that means that F2 must be 0, otherwise they are not exactly in series. But if you impose that condition, you can again get to the same system. And then if you remember, this system has these nice properties. It is symmetric, and its determinant is 0 again. Okay, so it has, it's now our global system, by the way. Again, see, we have jumped over node 2. It's just between nodes 1 and 3, but it has the properties you want. But also one interesting thing that now, if you're interested, you can see, if just for the fun of it, if you want to add F1 and F2 together. So let's say for some reason you want to add these two together. So F1 plus F1 and F3. If you add these together, you also get 0, right? So which makes sense. So basically F1 plus F3 is 0, right? So this is your equilibrium. So basically you have two springs. You're applying F3 here, you're applying F1 here, and the sum of forces must be 0. Okay, so this is also coming out of the system, which is obviously related to the fact that we did not have F2. I mean, if you had F2, then F1 plus F3 plus F2 must be 0. Okay, so that equilibrium changes its nature. All right, so any question? Very good. So if you remember where we started this, and I'm going to come back to that slide again. It was this. So we wanted, based on what we know or what we have learned on how to handle one spring, we wanted to solve for two springs in parallel, two springs in series, and now we want to do this one, okay, which is neither parallel or nor series. So it's a more interesting problem and is different from what you have done. Again, in the past 1 hour, basically, we have spent too much time on this compared to what you have known before. But now it's the payoff time, basically, because the process that you will do, the procedure now is exactly identical to what we have done previously. And then now we can go to complex systems like the one that we see in front of us. And later we can extend this, of course, to 2D and so on. So let's look into this now. So the first thing you want to do is to, again, as we did previously for the other systems, is to number the nodes in the system, right? So let's call this node 1, and then again, this is an arbitrary process. You can call any node you want to be 1 or 2 or 3. These are usually related to, let's say, geometrical locations rather than, personal taste for numbering. Okay, so this is 1, 2, 3, 4, 5. So you have 5 nodes. You have 6 springs, and we want to calculate the stiffness. Now, what do you think would be the size of the stiffness matrix here?
5/5.
Yes. So thank you very much. So previously, if you look at these systems, In the first let me just go back to this. In the first system, we have 2 springs, 2 nodes, and the stiffness was 2 by 2. In the second system, we have 2 springs, but we had 3 nodes, and if you remember, the stiffness ended up to be 3 by 3. So the stiffness is following the number of nodes, not the number of elements, basically. And in fact, if we do the same thing here, you would have 5 by 5. By the way, I am saying number of nodes, but this is not very correct. This is number of nodes times problem dimension. Here, problem dimension is 1. So number of nodes is 5. You get stiffness that is 5 by 5. If you were in a 2-dimensional space, then for 5 nodes, you get a stiffness of the size 10 by 10. If you go for 5 nodes to 3-dimensional problem, you get 15 by 15 for the stiffness. Okay, so the size of the stiffness matrix is always something like, let's say, a number of nodes times problem dimension times the same thing, obviously. So before you do anything, it's going to be a square matrix. So it's number of nodes times problem dimension. Okay. And by the way, just since we are doing this, I should also mention that in the previous system, or in the previous example, I mean, if you look at this, this is your system, and this is your system too. Okay, so later we will learn that we call this thing reduced system. It's a brutal simplification. This is not exactly reduced system. Reduced system is something else, but it's something like this. So it's a system that it has a size reduction. The idea of reduced system is a different thing, but the outcome is maybe not so different. But anyway, you can see that also in this system, for instance, if you look at the stiffness, this would have been also symmetric, and determinant would have been 0. So this is what we are talking about. This is the stiffness without imposing any constraint, without imposing any condition from boundaries. So we don't say what is where the forces are 0 or where the displacements are 0 or prescribed. So your raw stiffness, basically, not the stiffness after some manipulations. Okay, so again, this is like a raw stiffness dimension. And then as I mentioned, usually we do some magic later that we will learn, and we call that reduced stiffness. But anyway, the symmetry property would hold always. Okay, so in this example, it's 1D, so we have 5 nodes. We need a stiffness matrix, or we end up with a stiffness matrix that's going to be 5 by 5. So I think you can see this little, or the grid line on my tablet. So we use that as counter. So let's say this would be node 1, node 2, node 3, node 4, and node 5. Okay, so basically we are going to have a stiffness here. 5. Okay, does that make sense? So basically we have this empty boxes here. We have 25 of them, and we want to fill them according to our stiffness. Okay, this is going to be our stiffness matrix. So this is a system that is of the size 5 by 5. And this is going to be our, let's say, global stiffness, which, by the way, if I just want to, let me just write a simple version of it. So if you think of it, it's like this. You have F1, F2, F3, F4, F5. Equals those components of the stiffness, so that stiffness that is 5 by 5 times U. So you would have again U1, U2, U3, U4, and U5. And this stiffness components, it would be like K11, K12, K13, K14, and K15. So the first index is like the row counter, and then this is K21, K22, K23, and so on. And then here you have K31, K41, K51. Okay, so I'm not going to write all of it, obviously. And then here at the end, you have K55. So this is going to be your system. And then this stiffness is exactly what we have up there. So let's call this K. And then eventually the system we are looking at is exactly the same thing as we mentioned before, is equal F equals KU. Okay, so we are exactly talking about the same thing. Now, before going to the stiffness part, I want to ask you about the force part, because remember we played this game on forces previously. So here on point 2, 3, and 4, the forces are 0. It's a problem definition. They don't have to be. If you had an external force, of course, you just enter the value there. But in this case, we actually know that F2 is 0, F3 is 0, F4 is 0. Okay, so this is sort of a constraint to the problem so that you can solve it and you can get a response. And then for now, we just solve it for a usual system with different Ks, but later we assume that all the Ks are equal and they are all being 1 for simplicity. But let's just look at it now this way. Okay, so what do? We should go, let's say, point by point, or we have two options, by the way. Either we go point by point, or either we go element by element. Okay, so let's say you can come to this element, calculate its stiffness, and then enter where is appropriate. That's element-wise assembly. But you can also come to this point and see which elements are attached to it. Okay, so at node, or at point 3, or at node 3, you have 3 springs attached to it. At point 4, you have 3 springs attached to it. At node 2, it's also 3. At node 5 is 2. Does that make sense? So basically, you can do it also node-wise and then play with that. So I'm going to do it element-wise now, and then also usually in programming, that's the common way of doing it. And also I do one more, I add these virtual counters here for our own, let's say visual purposes. But then, so this is 1, 2, 3. We will remove them eventually, but let's say they are here to help us counting or not missing their rows and columns. Okay, so this is what it is. Now, for element 1, and I'm going to use different colors again for different elements for clarity. So I'm using this blue for element 1. Okay, so this is everything that comes from element 1. So element 1 is between node 1 and 2, and its stiffness is going to be K. It's our usual stiffness, K1 minus K1 minus K1 and K1. Okay, so what you want to do is to bring that thing into the box of 1 and 2. So let's say if you think of this square, this is what we want to do. This is where 1 and 2 should enter, right? So you put K1 here, minus K1, minus K1, and K1. Okay. Now let's do 2. For 2, I'm going to use, I don't know, the color green maybe. So I use this green here. Now, element 2 is between nodes 2 and 3. So now you are going to have a square which would be here. Okay, so now you need to do that. So basically, if you add that square, you would have K2 minus K2 minus K2 and K2. Okay, so you can see that on this square at node 2, for instance, just now, you have K1 from string 1, you have K2 from string 2, so they are going to add together. So we are going to add them up. We are going to assemble them basically, right? And which is no surprise. You can see node 2, it has one leg on spring 2, it has another leg on spring 1, but another leg on spring 5 too. So you shouldn't be surprised if you see a K5 also appearing here. Okay, so later, I am sure a K5 would also appear here because it's connected to spring 1, 2, and 5. Okay, so because the system gets complicated and crowded, I'm going to clean this and rewrite it smaller. But now I think you got the picture. And I also, obviously, I don't keep the squares anymore. So let me just do it now slightly smaller. So between 1 and 2, as we said, we have K1. So we have K1 minus K1 minus K1 and K1. But now on node 2, we also have K2. So we have plus K2. And then between node 2 and 3, you had plus K2, again minus K2, minus K2, and K2 here. So we come to spring 3, so this one, and I'm going to use orange for that. So spring 3 or element 3 is between nodes 3 and 4. So that's going to be somewhere here. So you get, again, plus K3 minus K3 minus K3, and then a K3 here. So that's a spring 3. Then I use this cool blue on 5, on 4 first. So spring 4 would be between nodes 4 and 5. So you would have now plus K4 minus K4 minus K4, and let's say K4. That's a spring 4. Then we have K5. K5 is between nodes 2 and 4. Okay, so it's going to be 4 components on these 4 squares. Okay, so this would be like K5. This would be minus K5. This would be again K5 minus K5, and this would be K5. So we need to add these into these boxes. So that's what I'm going to do now. So you get a plus K5 here, minus K5 there, minus K5 here, if I'm not mistaken, and then a plus K5 here. All right, we have one last spring left. We don't have many colors left. Yeah, how about this gray? So I do the last one with this gray color, light gray, and then that is K6 between nodes 3 and 5, and nodes 3 and 5 are basically this. So this would be the 4 corners of that square. So if you think this is K6, these 4 corners of K6, which would be basically K6 minus K6 minus K6 and K6, they enter here. So this square comes here, this square comes here, this one comes there, and the last square comes there. Okay, so this was here, for instance. So that's exactly what we are going to do. And as I mentioned, it's between 3 and 5. So you would have now plus K6 here, minus K6, minus K6, and plus K6. Okay. So this is your stiffness, and then everything else that is not filled, it is 0. And now you should have a good feeling about, or good understanding of those zeros, because you can see the places that are non-zeros, they tell you there is a connection between those 2 nodes. Okay, so basically this connection between node 1, 2, it is non-zero. That tells you that between points or between nodes 1 and 2, you have a spring. Okay, or let's say here, this is 3, 5. It is non-zero. It tells you between point 3, between node 3 and node 5, there is a spring, which is, right? So here you have a 0. That 0 means that between point 1 and point 3, there is no spring. And you can see there is none. Okay. And if you had, if you had a spring like this, let's say K7, then that would have come here. You would have like a minus K7 there. Okay. So this is basically telling you where the springs work, what is the domain of, what is their domain of influence. And then when they don't work, of course, you don't have them. And again, if you look at the system, it's again symmetric and its determinant is 0. All right. Is that clear? So let me just clean it up a little. So again, this numbering on the side, it was only for our own, let's say, learning purposes or teaching purposes. In this case, we don't need those numbers. So this is going to be your stiffness. Now, if you insert that stiffness here, and you impose the F's, you can calculate the U's. So that's pretty much it. But we want to simplify this. Let's now simplify this for a case that all the K's are identical. They are all 1. So let's say K1 equals K2 equals K3 equals K4 equals K5 equals K6 equals 1. So we want to do the simplification to just being able to solve this problem. And if you do that, now we can write the stiffness again. So basically, here you have 1, then you have 3, 3, 3, 2. So on the main diagonals, you would have 1, 3, 3, 3, 2. One, 3, 3, 3, 2. And then on these other ones, you have minus 1s here. I go step by step so that I don't miss something. And then here and here, they are also minus 1. Okay, now you have the system. So if you play the same game as we played previously, so if you impose these, you can connect the displacements of node 5 to node 1, and that would be your effective spring, right? So that is how we define the effective spring. So basically, the question is, if this is node 5, and this is node 1, in between, you should have an effective stiffness, right? So you have F5 here, and you have F1 here. What would be that, right? That is what we asked ourselves previously. And if you have done that for this example, so let me just do it in a different slide. So if you do this for the example here, you would end up with a system which is going to look like F1, F5, (1.5) minus 1.5 minus 1.5, 1.5, U1, U5. Okay, so basically this tells you that effective stiffness is 1.5. Okay, or otherwise it tells you I mean, this is clearly from the system. We can see, for instance, you can say F5 is 1.5 U5 minus U1. And this is your usual understanding of spring, right? I mean, if spring stiffness or spring formula is usually F equals K U, and there U is the stretch of the, or the change of length of spring. So that change of length, which is delta U, is U5 minus U1. So the effective system of the effective stiffness of the system in this case is 1.5. Okay, so we answered that question too. All right, so let me just sort of go back to where we started this. So remember, this is the first slide we started from. We said, based on what we have learned on springs, what we want to do is now to calculate the effective stiffness for two springs in parallel. Then we want to calculate them for two springs in series, and then something more complicated, which we also did. Okay, so now we know how to calculate the effective stiffnesses. And then again, I emphasize the goal here is not to play with stiffnesses. The goal was to learn assembly process. And what we did here, this process of adding these stiffnesses, this is exactly what we call assembly process. And I don't think there is a better way of teaching it. So this is a kind of simple way of teaching it. And I bring this slide and I finish the lecture with this slide to kind of identify that. The idea here is that you want to understand it enough and you want to explain it well. And if you want to explain it well, you should explain it simply. And I think this is the nature of our approach to finite element method in this course. We are not trying to make it complicated. We are trying to understand it. We are trying to understand every steps and then program our own finite element method, which I think only then, when you program it yourself, you very well understand these ingredients and pieces and how they match together, and then they make the big puzzle of the finite element method. What we want to do in the next lecture is to continue on the same line, but then we want to go to, let's say, understand how we can make this automatic. I mean, this was very nice. We understand how it works, but it was visual. We took advantage of the fact that the system was simple and we are looking at it. But then if you want to define it in your code, your computer should do this for you. So we want to make it automatic. We want to automatize this. Yeah, if that's the word. Yeah, so do you have any question?
I have a question.
Yes.
I don't understand the last part. Where do we come from 1 point? How do we find 1.5? I understand the matrix, but at the end, I missed that part.
Well, maybe actually you didn't miss it because I didn't exactly do it. This is just a mathematical step in between. So again, as I mentioned, I didn't exactly do it. So you have this system, right? Do you see this one? So you have a K and it's full of numbers basically. So you insert this here, and then you put these things, you set this to 0, right? And then you just calculate for U1 and U5. So you basically calculate the first row and the last row, you know, and then so it's a mathematical step. You just manually do it, or you I don't know, you do it with MATLAB or something.
Okay, thank you.
Does that make sense? Thank you very much for the question.
Jam, may I ask a question?
Yes, please.
We assume that stiffness is constant. For example, the stiffness changes with temperature. What would we write instead of the constants? Would we write functions or any other thing?
Yes, I mean that is actually kind of one of the very nice thing about the finite element method, that the physics is not entering too much into the mathematics of the problem. So exactly as you said, in this, I mean, everything that you have here it doesn't assume that the stiffnesses are constants. You know, they are it assumes they are numbers or they are functions. But as you said, I mean, K6, for instance, it could be a function of temperature. It could be a function of deformation. You know, it could be a function of anything, but it's still a number and it's still entering exactly where it is in the system. Does that make sense?
Yes, thank you, Hocam.
Sure. Any other question? All right. So thank you very much again for your attention. And as I mentioned, we will continue on assembly. So we will spend a little more time on assembly with the idea of making it automatic. Okay, so we want to just understand it well enough or simplify it enough so that the computer can understand it, because then computers are not smart, as you know. So we need to do the job for them. Very well. Thank you very much. And we will see us next week. Have a good weekend. Bye-bye.
See you, Hocam. Take care.
See you hocam.